In section 7.2, we will look at similar polygons. So in math, similar refers to two figures that have the same shape but not necessarily the same size. The symbol for similar is a squiggly line, and we can say that triangle ABC is similar to triangle PQR. Similarity ratio is the ratio of the lengths of corresponding sides. So if quadrilateral ABCD is similar to quadrilateral WXYZ, we can say that the measure of angle A is equal to the measure of angle W, and that if AD is to WZ, then BC is to XY. And that's because in similar polygons, corresponding angles are congruent and corresponding sides are proportional. So we will be able to set up proportions to solve for missing sides in similar polygons. Okay, we're going to look at two examples and determine if the figures are similar. So remember that in order for two pairs of figures to be similar, their corresponding sides are proportional and their corresponding angles are congruent. So in number 1, we are going to find out our similarity ratio for each pair of corresponding sides, and if it's the same for each pair, then our two figures are similar. So we can say that PI is to CO, so 5 is to 3.75, and this reduces to 1 1/3 or 4/3. We can say PG is to CW, so that's 10 is to 7.5, which reduces to 5 to 3.75 or 1 1/3. And finally, IG is to OW, so 8 is to 6, which reduces to 4/3, which is 1 1/3. So our two figures are similar because our three pairs of corresponding sides are proportional. So yes, our corresponding sides are proportional. All right, let's look at number 2. And in number 2, we see right away that angle P is 100 degrees, angle J is 120. These are our corresponding angles, and they are not congruent, so I know that my two figures are not similar, so no, because our corresponding angles are not congruent. Okay, and that's all we have to do for number 2. If our corresponding angles are not congruent, we're done. We're going to look at some examples where we use similar figures to find missing lengths. And we can set up proportions in order to find our missing sides. So in number 3, I can say that AC is to YZ as BC is to XZ. So let's substitute in our values. X is to 40 as 12 is to 30. And then we take our cross product. 30x equals 480. Divide by 30, we get x equals 16. So the length of AC is 16. Okay, number 4, we will find TS, which I will call X, and SR, which I will call Y. Okay, let's find TS first. So we can say ON is to TS as LM is to QR. So 2 is to x as 5 is to 6. So we get 12 equals 5x. Divide by 5, we get 2.4 equals x. So TS is 2.4. And then let's solve for SR. So it does not matter if we use our new value or we keep with our given values. So I can say that an M is to SR as LM is to QR. So 3.2 is to Y as 5 is to 6. Okay, then taking the cross product, we have 19.2 equal to 5y. Divide by 5, we get that y equals 3.84. So SR is 3.84. Okay, and in number 5, it says a painting is 24 inches wide by 36 inches long. The length of a postcard reduction of the painting is 6 inches. How wide is it? So if you want, you could draw a picture of this. So we have a rectangle painting. It's 24 inches wide, 36 inches long, and then we have a postcard of it. The length is 6. We want to know the width. So we can set up a proportion here. I can say 24 is to x, so I can say the length of the width of the painting is to the width of the postcard, as 36 is to 6. The length of the painting is to the length of the postcard. Then taking the cross product, 144 equals 36x. You divide and get 4 equals x. So our width is 4 inches. The golden rectangle is the rectangle that can be divided into a square and a rectangle that is similar to the original rectangle. Golden ratio is the ratio of the length and width of the golden rectangle, and it is about 1 to 1.618. So we will be able to use the golden ratio to find missing lengths of some of our figures. The golden ratio is considered the most pleasing ratio to the human eye. It appears multiple places in nature, architecture, and art. Some examples include snail shells, human body and facial proportions, credit cards, driver's licenses, the Parthenon, and pyramids. We're going to look at a few examples where we use the golden ratio to find our missing lengths. So in number 6, it says the length and width of a rectangular tabletop are in the golden ratio. The shorter side is 40 inches. Find the longer side. So our golden ratio is shorter side to longer side, and that's 1 to 1.618. So we have shorter over longer. So then my other ratio will be 40 over x, shorter side over longer side. And then just take the cross product, and we get that x equals 64.72 inches. So our longer side is 64.72 inches. In 7, a golden rectangle has a shorter side of length 20 centimeters. Find the length of the longer side. So same thing again, we will use our golden rectangle ratio. So 1 to 1.618. So we have shorter side over longer side, and our other ratio will be 20 over x, shorter side to longer side. Cross product, we get x equals 32.36 centimeters for the longer side. let's look at our last example. An artist plans to paint a picture. He wants the canvas to be a golden rectangle with its longer horizontal sides 30 centimeters wide. How high should the canvas be? So remember, our golden ratio is 1 to 1.618, and it says the longer horizontal side is 30. So we don't know how high it should be. I'll call it H for the height, but our longer side is 30. So if we take the cross product, we get 1.618 H equals 30. Divide by 1.618, and we get our height will be 18.5 centimeters. Okay, and that's our last example for section 7.2, similar polygons.